Cascode stage. As mentioned in example, the input signal of a common gate stage may be a current. We also know that a transistor in a common source arrangement converts a voltage signal to a current signal. The cascade of a CS stage and a CG stage is called a cascode topology, providing many useful properties. Figure shows the basic configuration. M1 generates a small signal drain current proportional to V in, and M2 simply routes the current to RD. Here you can see the figure cascode stage. We call M1 the input device and M2 the cascode device. Note that in this example M1 and M2 carry equal currents. As we describe the attributes of the circuit in this session, many advantages of the cascode topology over a simple common source stage become evident. First, let us study the bias conditions of the cascode. For M1 to operate in saturation, Vx greater than or equal to Vin minus Vth1. If M1 and M2 are both in saturation, then Vx is determined primarily by the term cascode is believed to be acronym for cascaded triodes, possibly invented in vacuum tube days. Vb is to Vx is equals to Vb minus Vgs2. Thus Vb minus Vgs2 greater than or equal to Vin minus Vth1, and hence Vb greater than Vin plus Vgs2 minus Vth1. Figure for M2 to be saturated. For M2 to be saturated, V out greater than or equal to Vb minus Vth2, that is V out greater than or equal to Vin minus Vth1 plus Vgs2 minus Vth2 if Vb is chosen to place M1 at the edge of saturation. Here you can see the figure allowable voltages in cascode stage. Vth2 if Vb is chosen to place M1 at the edge of saturation. Consequently, the minimum output level for which both transistors operate in saturation is equal to overdrive voltage of M1 plus that of M2. In other words, addition of M2 to the circuit reduces the output voltage swing by at least the override voltage of M2. We also say M2 is stacked on top of M1. We now analyze the large signal behavior of the cascode stage shown in figure as Vin goes from 0 to VDD. For Vin less than or equal to Vth1, M1 and M2 are off. V out equal to VDD and Vx is similar to Vb minus Vth2. If threshold condition is neglected, figure as Vin exceeds Vth1, M1 begins to draw current and V out drops. Since RD2 increases, Vgs2 must increase. Here you can see the figure input-output characteristic of a cascode stage as well, causing Vx to fall. As Vin assumes sufficiently large values, two effects occur. One, Vx drops below Vin by Vth1, forcing M1 to the triode region. 2, V out drops below Vb by Vth2, driving M2 into the triode region. Depending on the device dimensions, the values of Rd and Vb, one effect may occur before the other. For example, if Vb is relatively low, M1 may enter the triode region first. Note that if M2 goes into deep triode region, Vx and V out become nearly equal. Let us now consider small signal characteristics of a cascode stage. Assuming both transistors operate in saturation, if lambda equals 0, the voltage gain is equal to that of a common source stage, because the drain current produced by the input device must flow through the cascode device. Illustrated in the equivalent circuit of figure, this result is independent of the transconductance and body effect of M2. Here you can see the figure, small signal equivalent circuit of cascode stage. An important property of cascode structure is its high output impedance as illustrated in figure. For calculation of R out, the circuit can be viewed as a common source stage with a degeneration resistor equal to R01. Thus, from equation R out equal to 1 plus GM2 plus GMB2 into R02 into R01 plus R02. Here you can see the figure, calculation of output resistance of cascode stage. Here you can see the figure, triode cascode. Assuming GM are not greater than 1, we have R out similar to GM2 plus GMB2 R02 R01, that is M2, boost the output impedance of M1 by a factor of GM2 plus GMB2 R02. As shown in figure, cascading can be extended to 3 or more stacked devices to achieve a higher output impedance, but the required additional voltage headroom makes such configuration less attractive. For example, the minimum output voltage of a triode cascode is equal to the sum of 3 overdrive voltages. To appreciate the usefulness of a high output impedance, recall from the lemma in session that the voltage gain can be written as GM R out, since GM is typically determined by the transconductance of a transistor, example M1 in figure, and hence bears trade-offs with the bias current and device capacitances. It is desirable to increase the voltage gain by maximizing R out, shown in figure is an example if both M1 and M2 operate in saturation. Here you can see the figure, cascode stage with current source load, and GM similar to GM1 plus R out similar to GM2 plus GMB2 R02 R01, yielding AV is equal to GM2 plus GMB2 R02 GM1 R01. Thus, the maximum voltage gain is roughly equal to the square of the intrinsic gain of the transistors. Here you can see the figure, increasing output impedance by increasing the device length or cascoding. It is also interesting. It is also interesting to compare the increase in the gain due to cascoding with that to increasing the length of the input transistor for a given bias current. Suppose, for example, that the length of the input transistor of a CS stage is quadrupled while the width remains constant. Then, since ID equal to 1 by 2 nu C0 x W by L VGS minus VTH whole square, the overdrive voltage is double and the transistor consumes the same amount of voltage headroom as does the cascode stage. That is, the circuits of figures B and C impose equal voltage swings constraints. Now consider the output impedance achieved in each case. Since GM are not equal to root over 2 GN C0 x W by L, ID into 1 by lambda id, and lambda inverse proportional to 1 by L cubing. L only doubles the value of GM R naught, while cascoding results in an output impedance of roughly GM R naught whole square. Note that the transconductance of M1 in figure B is half that in figure C, leading to higher noise. Chapter a cascode structure need not operate as an amplifier. Another popular application of this topology is in building constant current sources. The high output impedance yields a current source closer to ideal, but at the cost of voltage headroom. For example, current source I1 in figure can be implemented with a PMOS cascode exhibiting an importance equal to 1 plus GM3 plus GMB3 R03 into R04 plus R03 if the gate bias voltages are chosen. Here you can see the figure. NMOS cascode amplifier with PMOS cascode load. NMOS cascode amplifier with PMOS cascode load. Here you can see properly the maximum output swing is equal to VT minus VGS1 minus VTH1 minus VGS2 minus VTH2 minus mod VGS3 minus VTH3 minus mod VGS4 minus VTH4. We can calculate the voltage gain with the aid of the lemma illustrated in figure, writing GM similar to GM1 and R out is equals to 1 plus GM2 plus GMB2 R02 R01 plus R02 1 plus GM3 plus GMB3 R03 R0 into R04 plus R03. We have mod AV similar to GM1 R out for typical values. Approximate the voltage gain as mod AV parallel to GM1 GM2 R02 GM2 R02 R01 parallel to GM3 R03 R04. Shielding property. Recall from figure that the high output impedance arises from the fact that if output node voltage is changed by delta V, the resulting change at the source of the cascode device is much less. In a sense, the cascode transistor shields the input device from voltage variations at the output. The shielding property of cascodes proves useful in many circuits. The shielding property of cascode diminishes the cascode device enters the triode region. To understand why, let us consider a circuit in figure assuming Vx increases from a large positive value as Vx falls below VB2 minus VTH2. M2 requires a greater gate source. Here you can see in the figure output swing of cascode stage overdrive so as to sustain the current drawn by M1. We can write ID2 is equals to 1 by I2 nu n C naught x W by L2 2 into VB2 minus VP minus VTH2 into Vx minus VP minus Vx minus VE whole square. Concluding that as Vx decreases, Vb also drops so that ID2 remains constant. In other words, variation of Vx is less attenuated as it appears at P. If Vs falls sufficiently, Vb goes below VB1 minus VTH1, driving M1 into the triode region. Thank you.